Hey everyone, and welcome back to the channel. Today I'm very excited to make a video actually doing some technical stuff of my own as opposed to just regurgitating other stuff that people have made in the past. I've really been looking forward to doing this type of thing for a while, so I hope that you guys enjoy it. I'm hoping the recording quality of this video comes out okay, but as you can see it's pretty dark in my apartment and my lighting's kind of shitty. So I swear I'm not in a sex dungeon, this is just what my place looks like. Anyways, we're going to try and get into a little bit of a design doc that I've written, kind of a continuation from last video, and then my hope is that I can actually get coding on this thing fairly soon. But I hope you guys enjoy, and I will see you when I have the document up. Okie dokie, so I've got everything up. I'm not planning on doing a lot of editing in this video because I just hate doing that, and I prefer to talk about technical stuff. So I'm sorry if it takes me a lot of time to do this, or maybe I ramble a little bit, but basically I just want to go through this document on the left, and then I've also made some images on the right, which I'll eventually incorporate into it, but you know, my goal is to just kind of present this problem and maybe a viable solution to it in a way that everyone can understand. And you know, get myself excited for it, and hopefully also some viewers as well, because that's really what I care about too, is building this thing and having the motivation to do it from you guys, and you guys are always great about that. So let's go ahead and talk about it. Basically, long story short, as I kind of alluded to in the last video, you've got a bunch of modern data table formats, right, for big data. Things like Iceberg, Hudi, and Delta Lake. And the idea is that they pretty much do this thing called object store for everything. They generally don't incorporate any databases whatsoever. Pretty much all data as well as metadata are just files on an object store. Now that in theory is good, right? Like the data itself should probably be in Parquet files. That is the fastest and best known way of reading analytical data. You want something that's highly compressed, columnar, and Parquet is really, really good for that. And I don't think anyone is going to disagree with that's what you should be doing. The problem is now is that you've got all of these kind of low latency, high throughput data pipelines that exist where people want to see their data quickly in these data lakes. And the problem is that now object stores are getting used for things they shouldn't be. They're getting used for high frequency updates of data, high frequency deletions of data, and the problem is that these Parquet files that exist are inherently immutable. And so we're going to go into what that means in a second. So let's take a look over here at figure 1. Basically, long story short, if I'm over here, I'm going to go ahead and just draw out circles. And then I'm going to drag myself over a little bit. So basically, if we're in Iceberg, right, and we have this data file, which I'm demonstrating on the left, the first thing that I'm going to do is I want to go ahead and set one particular column of one row. Let's assume it's a pretty wide table, right? So wide means there are a lot of columns in this table. The first thing that I have to do is really annoying is one way or another I'm going to have to upload a new version of the row right over here. And when I upload that new version of the row, I need to upload the full thing. I can't just upload the change column, which is really freaking annoying, and it's something I deal with on a daily basis. Number 2 is that you now make a choice between two types of deleting the old version of the row in Iceberg. Option 1 is you can do a position delete, and option 2 is you can do an equality delete. So basically the difference between these are that position deletes are write optimized, meaning I don't have to actually read through the existing data to perform a position delete. I basically just say, hey, here are the criteria that are going to make it so that I can delete this row. And in this case, what that basically means is just very simply put, we're going to delete all the rows where the ID is Y. Similarly, although a little bit different, is the equality delete. Sorry, God, I mixed these two up right here. This should be the equality delete, brutal, and this should be the position delete. Like I said, no edits though. So anyway, the point is, the position delete, on the other hand, is where you actually point to a position in a particular file and you now say that's deleted. So as I'm sure you can imagine, that's going to be a lot more efficient at query time, because now when we're actually reading through this data file right here, I can basically say, oh, wait a second, this is the row that's at position 1 in file A. I'm now just going to not regard this thing. And so that's a lot faster than evaluating every single data file against this equality delete. There's a lot more read amplification would be the term that people use. So basically you have these two choices in Iceberg, and at the end of the day, neither of them are pretty good. Both of them offer a lot of constraints, and basically whether it's the equality delete or the position delete, you have to wait for data to get compacted before anything is going to really get better in terms of read or write performance. So let's move on in this document a little bit. So we discussed Iceberg and how it's really not right optimized. That being said, there's another table format which kind of tries to fix this, which is called hoodie. So I've spoken about hoodie on this channel as well, and basically the idea there is that there are a couple of optimizations here. For one, in hoodie, you have this concept of an index. So the index is basically a high-level mapping of a particular record by its key that you're generally going to be trying to update it on, and which file group it's in. So a file group in hoodie is basically saying, like, okay, you've got this thing called a base file. Oh boy, let me drag myself back over. You've got this thing called a base file, and the point of the base file is to say, like, hey, these are the initial records that we published. But then also, if you're going to make a bunch of small changes to it, for example, modifying one row at a time, you might want to publish a delta file that has some modifications for rows in that base file. So for example, when we come along and we say, all right, I want to take one row where the ID is equal to y, and I want to set one particular column of it, x, equal to x plus 1, what we can actually do in hoodie, first off, is only publish the tuple that looks like something like y comma x plus 1. So we don't have to publish every single column of the row again, which is good. This is just going to save us a lot of time writing data if it's a wide table. But also, more importantly, we have this index, right? So in hoodie, there are multiple different types of ways of representing this index. But the idea is that we can basically take a look at, which file group this row is in. And so that way, it's basically like a more right optimized position delete, because we're basically putting the delta file that we're writing in the right place, right? We know it only corresponds to this file group A right here. But because we have this index, we now don't have to search through a bunch of files, figuring out which file group and which position a given record belongs to. We only have to look through the one file group itself that it belongs to, and now we can make a more efficient modification or delete in hoodie. So there are multiple different ways of maintaining this index. Basically, there's something where you can actually just keep track of every single record in the file group that it's in. That's called a record index. There's something known as Bloom filters, which is basically you are centralizing all the Bloom filters and all the Parquet files to give you a better idea of which file groups a record could potentially be in. So that's a probabilistic type of thing. And then you've also got expression indexes, which are almost like equality deletes, but it's basically saying like file group A contains all rows from A through C or something like that. All rows with ID A through C. So the idea is that hoodie is trying to make writes better. But at the end of the day, when you're reading data in hoodie, until it's compacted and until this delta file gets merged back into the base file, we still need to resolve these two things with one another. And so it's great that you now have this right optimized pipeline, but at the end of the day, you've got a bunch of small delta files that need to get merged back into your file. And it's ultimately just not going to be as efficient as a normal database, right? And this is the problem that people keep running into with all these lakehouse tables, is people are trying to kind of figure out a way to get database-like write performance over immutable files, and that's just physically not possible, right? We're trying to do too much. And so now that's kind of something that people are coming to the realization of, right? Like in hoodie, you're effectively executing a join on each query to handle table update rows. But that's just not really going to be fast enough at read time. So now you're sacrificing read performance, which was the whole point here. We wanted this analytical store to be super fast for big reads. So again, a database is going to do this type of thing better. Even besides that, when you have every single write to an Iceberg or a Delta Lake or a hoodie table, and it's always creating a bunch of small files on object store, that's really going to add up over time. I think, if I'm correct, every 1,000 put operations in AWS is that many dollars. And then I believe that get operations are 1/10 of the cost of put operations. But the point is, these costs really add up over time. They're not insignificant. If you're going to make a bunch of small writes, you're not supposed to be doing it to an object store. That is like the antithesis of the proper architecture here. And so now, people are starting to think, well, why don't I use a database for my metadata instead? And we'll talk about that in a little bit, but that's kind of the idea. So now what's happening instead is, we have all of these engineers that are basically saying, all right, screw this. I know that certain data is going to get updated a lot. I'd rather just keep that in a normal database. And then I would, keep all of that data that's getting updated a lot in the database. And I have all of my analytical data that's not going to be updated very frequently in an Iceberg table, and I'm just going to merge those together when I query the data. And that's good, but it has some edge cases. So basically the idea is that now we're doing query federation, but all of these things that do query federation are not really allowing point-in-time snapshotting of the data. And that's what that means, is that you can't really transition a batch of data from the database to the iceberg table or something like that without there being some sort of weird edge condition. So let's demonstrate those. So let's imagine I'm doing query federation here. I now have something like Trino, which is up at the top of my screen. Trino is going to be reading both the database, where we've got data that's getting updated a lot, and iceberg, which is kind of containing all the immutable data. And so first what's going to happen is, imagine we have some batch job that comes along, right? And the batch job is basically saying, all right, we've got some data in our database now. We want to move it to the iceberg table because our database is filling up. And even besides that, these rows aren't really getting modified anymore. So it's going to read some data from the database. It's going to put that data in the iceberg table. And that's all good and well, right? However, before it can actually remove that data from the database, now what's going to happen is maybe a Trino query comes along where it's going to read from the database and it's going to read from the iceberg table at the same time. And now we're in a state where we can see duplicate data. So the opposite of this would be where we actually remove the data from the database before we write it to the iceberg table. And then Trino would actually, instead of seeing duplicate data, it just wouldn't see that data at all, which would be equally problematic. So either way, because Trino is capable of reading this data in a non-transactional manner, because the batch job can't transactionally commit between the database and iceberg, we kind of have an issue when it comes to building out these federated systems. That's issue number one. Issue number two is that you can have schema evolutions between them, right? So let's say the database, someone adds a new column to it, and then eventually that column will get added to the iceberg table, or vice versa. Trino is going to read both tables. It's going to try and union them together or something. And what might happen is, because those schemas aren't identical, depending on the engine, you may error out. I am not as familiar with Trino. I use Dremio a lot, but the idea is, if Dremio sees two schemas that are not identical and you try to union them together, it's going to throw an error and it's going to be upset. So what we lack is one sort of centralized way of, atomically committing data from here to here. And we also lack a way of atomically modifying schemas for both here and here at the same time. And even still, even if we were able to build that out and make it work with Trino, what about making it work with Spark? What about making it work with Flink? What about making it work with Presto? So the point is, we want one sort of centralized layer that's going to allow giving a unified view over all of these different types of data stores. So those are a couple of the problems that I named right there. Let's continue through this design doc. Basically, another problem, even besides the idea of federation in general and the issues with that, is just going to be data streaming. So basically, when it comes to streaming data into Iceberg, one very common pattern to doing so is using Apache Flink. So maybe you'll take in some rows from Kafka into Flink. Flink is going to eventually persist them to Iceberg. And every once in a while, your Flink streaming job is going to persist checkpoints, right? Because if for some reason Flink fails and then comes back up, we don't want to persist duplicate data from Kafka to your iceberg table. And we also simultaneously want to make sure that every row that is in Kafka is in the iceberg table at least once. So the problem here is actually a very similar one when you break it down to our problem with Trino, which is that Kafka has a way of managing its own offsets and Iceberg has a way of managing its own metadata, but there's no way to kind of centralize that. So instead, what you see Flink doing is running its own normal checkpoint algorithm, where basically every single Flink checkpoint is keeping a consistently aligned kind of state of both the iceberg table snapshot that corresponds to certain Kafka offsets that it's processed. So this way, if Flink goes down and it comes back up, it can restart, basically treating the iceberg state as it was, and then also resuming from those Kafka offsets and then continuing onwards, and that's how you get exactly once row processing, which is great. And eventually it's going to be taking those checkpoints and it's putting those in S3. Now that does work, and a lot of people are starting to use this, which is great because it's very common to go from Kafka to Iceberg. And maybe it's not Flink, maybe it's Kafka Connect. The idea is they'd be doing something similar. But the problem is, this is honestly a pretty simple pattern, right? Like, it's very common that people are going to have data in some sort of log-based message broker, have it in some sort of row-oriented format, like Avro, JSON, or protocol buffers, and then they're going to move it into a columnar format with Iceberg. And it really is not that complicated of a process, except now all of a sudden we need all these complicated streaming engines to actually perform this. Now, I personally have used Flink now a decent amount at my job, and I can say with certainty that it is a royal pain in the ass. Like, if I can avoid using Flink and just write my own Java application or my own Python application or whatever that's going to read rows from Kafka and commit them to Iceberg, probably a lot of the time I'm going to do so. Flink adds additional complexity. It's a little bit harder to monitor. You have to do a ton of configuration with it. There's a pretty steep learning curve. Same is true for Kafka Connect to some extent. Or just like you don't have as much freedom to mess around with the internals. Flink is really, really good for building complicated streaming pipelines, but it's not all that good for just doing like, hey, I'm taking rows from Kafka and I'm putting them in Iceberg. It's kind of overkill for that. So the point is, if Flink is kind of limiting you to like the JVM somehow, right? Like Java-based languages, so like Java, Scala, Kotlin or whatever, and maybe they have like some Python bindings too. But the point is, like, if I want to write my thing in C++ or I want to go write it in Rust or whatever, and I don't want to deal with Flink, too bad, like, so sad, you have to go do that. And so it's kind of a pain in the butt that we basically need some sort of checkpoint management streaming system in order to do all of this. You know what would be a lot easier is if we just had one single metadata layer, right? And rather than making that Flink specific, we just provide an API such that any sort of random application can subscribe to Kafka, persist to Iceberg, and then atomically update both the last Iceberg table snapshot as well as the last process Kafka offsets. For stateless applications where you're just taking Kafka rows and you're putting them in an Iceberg table, this is really all you need, and it is way too complex to have to get Flink involved in all of this, when all you really need to do is just have one simple API that can store both of those offsets for you. So I guess the point is, we've kind of overly complicated streaming by virtue of having all of these disparate systems and nothing that really ties them together. And that's a similar problem to what we saw with the query federation layer. So just to read through that section of the design document, offset management should be something handled at the table level. So in theory, actually, Iceberg and Hoodie, I think, or definitely Hoodie, maybe Iceberg, let you just put arbitrary stuff in the table metadata. So you actually could put in the Kafka offsets as well that correspond to the table state and then restart from there. But even besides that, even if we could do that, what if we actually just want to read data from Kafka as part of our table, right? We don't just want to have exactly once processing into the Iceberg table, but we want data to be part of our Iceberg view or like readable the second it gets into Kafka. Then just being able to implant those offsets in the Iceberg metadata is not nearly good enough for us. And the same thing goes for if we wanted to, have a database as part of our Iceberg table. Right now, that's just not possible. So let's continue down a little bit. Basically, what we're looking to build is something known as an HTAP, so Hybrid Transactional Analytical Processing. You have the power of low latency writes by virtue of exposing data that's in Kafka. You have the power of quick modifications by enabling people to use a database. You have the power of, fast analytical queries over large sets of data by using things like Iceberg tables, Hoodie tables, Delta Lake tables. And at the end of the day, there needs to be some layer that ties those all together. So Databricks and I think Snowflake currently have their closed source proprietary versions of these. But at the end of the day, like with just about everything else, you probably want this to be an open standard, right? So that it works with every single sort of database engine and you don't have to go invest in one particular vendor and give them a ton of money and get locked in. So my goal is basically to build that format. You want to build one format that wraps around your Kafka queues, your Iceberg tables, your databases that are in your schema. And that way you can actually have engines like Trino querying all of these things in one place and knowing how to do so without having to add a bunch of extra headaches on the part of the user for all these race conditions that I outlined. Now it's worth noting as well that there are other table formats that have kind of come around recently. One of them is called Duck Lake. One thing that I personally particularly like about Duck Lake is that it ditches the stupid thing that I feel that Iceberg does, which is have all metadata still live as files on Object Store. Instead, Duck Lake just uses a transactional database, which achieves the same semantics as files on Object Store, but can achieve a much higher write throughput. And so it seems ultimately like we should be using a database to store our metadata for this thing that we're building as well, but I'll touch upon that in a little bit. So basically, to summarize what I've been ranting about in the last few minutes, there are basically three types of cases that I've already encountered in my own work that I feel like would be much more simple if something like this existed. Basically, I think, for one, there are a lot of teams that are starting to build federated data lakes, or HTAP tables of their own, where it involves some sort of Iceberg or Hudi or Delta Lake format, as well as a transactional database. And when you do that, the problem is that it doesn't work with every engine. You probably aren't getting snapshot reads unless you're being very, very careful about it. And you're not getting ACID compliance between the database and the lakehouse table. So I think this can improve upon that a lot. Number two is that teams have been forced to operate within the limitations of a lakehouse format when attempting data mutability. So basically, some teams are going to be brave and try to incorporate a database into their HTAP design. Others are going to try and be like Hudi and basically just try and figure this all out using a bunch of files on Object Store. I think that's a bad idea personally. I'm going through that myself at work, and I find that it is quite tough to execute. So you want to make the right decision, right? You have databases which exist for this sole purpose. There's no reason to try and force that to be an analytical system workload if you can avoid doing so and you have an easy way of doing so. Number three is teams that have been forced to use complex streaming tools just for the sake of taking something like Kafka data and putting it into Iceberg. You should be able to use any application that you want. You should be able to generate those files and convert them in any way that you want, performing any tweaks that you want. It shouldn't be abstracted away from you if you don't want that in a language that is not really of your choice. You should be able to use the deployment tools that you want and have the observability tools that you want. And the only thing that really needs to be standardized is the API where you kind of report the metadata of, hey, what offsets are currently valid for this table in the Kafka queue and what files in the Iceberg table are currently valid. Right? So basically the idea is, we have query engines that already exist that can perform federation. So let's go ahead and move on to this last diagram over here. I know this video is getting a little bit long, and I know that I'm ranting, but I'm having a good time. Hopefully you guys are having an okay time. Basically, the idea is this. If I'm a data analytics team, I probably am already using one of these tools, right? So I'm going to be using Trino, or I'm going to be using Flink, or I'm going to be using Spark, or I'm going to be using Presto to do my data analysis. I also probably have some sort of streaming pipeline to get my data into something like Iceberg eventually. Let me get rid of that arrow. That's a cheeky one. Point is, I have some data in Kafka, right? If that data in Kafka is getting modified all the time, right? So there are multiple versions of a particular row coming in and they're overwriting one another, modifying one another. I probably want to be putting those in a database and modifying them in a database. It is a lot more simple than doing so in an object store. So maybe that's where I put my hot data, and maybe I write a custom application to get it there, right? Then maybe from that database, after let's say a day, those rows stop getting updated, and I take that data and I use a batch job to put it into my Iceberg table, right? So here are three things that can be sources of data. I can read incoming rows from Kafka. I can read data that's being modified a lot from Spanner. I can read data that is kind of in long-term storage in Iceberg. And Trino and Spark and Flink and Presto pretty much already have the connectors to do all of those individual reads. The problem right now is that when you're reading from these, they tend to want to be reading them individually. If I want to read from both Spanner and Iceberg and do that in a way where I can be actively transitioning data between the two of them and getting snapshot consistency, I don't really have a good way of doing that at the moment. So basically, what Trino should first be doing is reading from this thing that for now I'm just calling the data harness, right? So Trino is going to go to the data harness and it's going to say, all right, table X, what are your sources? And the data harness is going to respond, okay, well, I've got Kafka as a source, I've got Spanner as a source, and I've got Iceberg as a source. And out of those three things, the offsets that are valid in Kafka are, A to B. Spanner has data up to time t, because Spanner actually makes all writes in the database linearizable. And then Iceberg is also valid as of snapshot time t, right? And so now, all of a sudden, Trino is able to read all of these three things as of those logical timestamps and get a consistent view across Kafka, Spanner, and Iceberg. Now, keep in mind that data is actively flowing between these three systems. So how do we ensure that we continue to get ACID compliance as that happens? Well, for one, when this consumer group takes data from Kafka and puts it into Spanner, Now all of a sudden the data is in Spanner and it should no longer be visible from the Kafka queue. So it's going to change the offsets that are visible in the Kafka queue down here by bumping the Kafka offsets and also bumping the Spanner timestamp and telling data harness about that. Of course, we can make that an atomic write because under the hood our data harness will probably be using some sort of ACID database. Additionally, we now have a batch job that, let's say once a day, is taking rows from Spanner and putting them into Iceberg. When it does that, it needs to now bump the timestamp after it writes the Spanner data, right? So it's going to remove some data from Spanner. That's going to now have a deletion timestamp. And let's say we delete data from Spanner, delete data at time X, and then we're going to add data to Iceberg at time Y. Only after both writes are completed are we going to go right to our data harness. Spanner is now at X, Iceberg is now at Y. And that gets updated atomically, this metadata. That means that the next time Trino reads, it's going to make sure to read Spanner data at time X and Iceberg data at time Y, and there's not going to be any sort of problem or race condition where they might be seen in an inconsistent state where we might get duplicate data or no data. So because we now have this one common data harness, which is keeping track of the valid offsets of all of our data sources, we can actually start building actual federated HTAP tables that are going to work across many different data sources. So just to quickly map out what this data harness spec is going to look like or something like that, very simply put, it's got two tables internally. You've got one table that is listing out all of the possible tables. So for example, I can have a table called federated, which is going to have some sort of schema because we need to keep track of that as well so that Trino knows what schema to query across all of them. And then from there, if we actually look at the sources of the table of the inner tools that make up the federated table, we've got one Spanner database, right? And we're going to query that as of time, whatever this is, on table X within Spanner. We've got one Kafka partition, so topic X partition Y. We know the two offsets to query between. Fortunately, Trino already has a Kafka connector, so there's not too much work to be done here. ADBC is one that maybe you haven't necessarily heard of, but ADBC is referring to Arrow database connector. So instead of JDBC, you're going to be getting Arrow flight data over the network, which can be good if you want to optimize for column-oriented reads. So maybe that would be helping us read from Snowflake or something at a particular timestamp. And then, of course, in addition to ADBC, we also just want to include actual data lakehouse formats as valid sources as well. So now we can have an Iceberg table. We can pass in the catalog URL. We can basically go ahead and now tell it which Iceberg table is part of our federated table, and then also the snapshot ID of the Iceberg table that we want to read. And so in conjunction, what's really happening is that Trino or Spark or Flink or Presto is reading from all four of these sources at the same time, unioning them together, federating the query, so pushing down whatever filters it can, and then returning the results back to the user. This is going to allow us to maximize liveness. It's going to allow us to write and modify data in the actual correct system as opposed to trying to force everything into Iceberg or Hoodie or Delta Lake. And overall, it's also just going to simplify the actual ingestion workflow because now we don't need to use Flink everywhere, Kafka Connect. We can just write our own applications and then update this data harness. So hopefully that kind of covers exactly what it is that I'm looking to do here and kind of the mission that I have because I'm suffering with this myself at work and frankly, I'm getting kind of sick of it. So I guess the question now comes up, well, what work actually has to be done here? It's not too hard to actually build this concept of a data harness or something like that, right? Which has these two tables. In fact, I could probably do that in a couple weeks, if not less. The main work here is actually just going to be modifying engines because at the end of the day, if we want Trino, Spark, Flink, or Presto to be able to kind of read the data harness, well, we now need to add extra logic into all four of these engines to be able to do that. And then we also may need to modify existing Kafka connectors, JDBC connectors, Iceberg connectors, Hoodie connectors, Delta Lake connectors to be able to do snapshot reads so that we can actually get snapshot reads across many different sources of a table. I hope this mostly makes sense to you guys. If anything didn't, I would greatly appreciate any questions that you have. and giving me any suggestions on how to improve things. Obviously, this is very early stages, and it's just a personal project. But yeah, at the end of the day, it's an issue that I'm passionate about, and I think it's one without a really good solution in the data community right now. So I'm really looking forward to building something that's hopefully not too much engineering work, but can be really impactful. Anyways, guys, as always, I hope that you all have a great day. We're getting pretty close to 100K, so hopefully by the video after this one, we'll be there. And yeah, it's just been a real honor. I'm really excited to move on to the next chapter of this channel. And you guys continue to really motivate me and push me to be the best engineer I can be, and I can only thank you for that. So have a great night.